Welcome to Hindustan video lecturing series. I am Santhana Krishnan, Professor, Department of Aeronautical Engineering. Today I am going to see, we are going to see the bending and shear stress variation in the beams. We will see what is this beam. So, beam is a structural member which can take transverse loads. So, this is a beam which can take the transverse load. So, this is the end support. So, this will take both horizontal as well as vertical reaction, and this will take only the vertical reaction. So, there are three unknowns here. The available equation of equilibrium is 3. So, this is statically determinate problem. Then we are going to see what is the bending and shearing stress in beams. First, before that we will see what is stress. The intensity internal resistance of body per unit area is termed as stress. So, normally what we will do, you take any structural member, it is subjected to the axial load. So, let us take a cross section here. We will draw the free body diagram. We will take divide this body into two. This is body 1, body 2. I will take body 1. I am going to show the internal and external force acting on the body, and this is resisted by this force. So, I can write stress equal to the resisting force by area. The next here bending stress. So, bending stress is a more specific type of normal stress. When a beam experiences a load like that shown in the figure, the top fibers of the beam undergo normal compressive stress. The stress at the horizontal plane of the neutral is 0. The bottom fibers of the beam undergo a normal tensile stress. So, we will see some preliminary concepts in before going to see the derivation of bending stress. The first one is called pure bending. When a segment of beam in equilibrium under the action of bending moment alone is called pure bending, or you can call flexure also. And this is a diagram of representing the pure bending. It is a simple beam, 2 point loads are there. So, in between you can see the sections shear force is 0 and the bending moment is constant. That is, at that portion the beam is in equilibrium under the action of bending moment. Then right hand rule. So, right hand rule applicable for force as well as moments. First, for force, the forefinger acting upwards and the center finger pointing towards you and the thumb finger is towards right. This is called right hand rule. Normally, this is used for force convention. Then next is moment and torque. What we are using is you have to curl the fingers like this, and this is the direction of the moment. And there are 3 basic assumptions in deriving the flexural formula. Number 1, the longitudinal axis x, which lies within the neutral surface, does not experience any change in length. Number 2, any cross section of the beam remain plane and perpendicular to the longitudinal axis during the deformation. And third assumption is the z axis lying in the plane of the cross section and above which the cross section rotates is called neutral axis. For example, if we take this is a beam and this axis is called x axis and this is your y axis and this is your z axis. The layer which is in between the top layer and the bottom layer is called neutral layer. That is only I have shown the neutral longitudinal axis x which lies within the neutral surface. So, we will take a horizontal beam with the vertical axis of symmetry. Here this is symmetry with respect to y axis, and I am applying a moment about the z axis. So, we will take various points A B is at the top of the fiber, and DC is the bottom layer, and EF is the neutral layer, and GH I have taken, that is just above the neutral layer, that is this layer undergo compression. And this diagram represents the neutral surface on neutral axis. And once you are applying a moment, here you can see it is a pure bending, only moment is applied, that is moment MZ. The beam undergo compression, the top layer undergo compression, whereas the bottom layer undergo tension. The layer GH, which is just above the neutral layer, that also undergo compression. If I want to measure the normal strain along the GH, I can find out strain equal to, that is change in length by original length. The change in length is nothing but the final length minus initial length by initial length. Then I can write rho minus y d theta, that is a final length, minus rho d theta is a initial length divided by initial length. You will be getting minus y by rho. I can say 1 by rho is nothing but k, that is called curvature. So, you can write strain is directly proportional to minus y. So, here after seeing this equation, you can say the longitudinal normal strain of any element within the beam depends on the location of y. Thus, the longitudinal normal strain vary linearly with y from the neutral axis. It is maximum at the extreme fibers. The contraction minus epsilon will occur in fibers located above the neutral axis, that is plus y. The elongation plus strain will occur in the fibers located below the neutral axis of minus y. And by using Hooke's law, we can write stress is directly proportional to strain within the elastic limit. I can write stress in x direction equal to E times of epsilon x. So, already we know epsilon x equal to minus yk. I can say sigma x equal to minus Eyk. So, here E and y are constant, E and k are constant. I can say sigma x is directly proportional to minus y. So, they can, from this we can depict that the stress is also directly proportional to y. And here the important point is location of neutral axis. So, normally we have to find out where is the neutral axis located. For that, what you have to do, take a small differential element of the cross section. So, I have taken a small differential element dA. So, in the dA, dF is the forces acting. The layer which is above the neutral layer is compressive forces, and the layer which is below the neutral layer is undergo tensile forces. So, the net force is 0, that is equation of equilibrium. If you add all the forces, it should be equal to 0. So, I have taken a small dF, that is equal to sigma x dA, then dF equal to minus Eky dA, and the net force equal to, you have to integrate over the area, you will be getting minus Ek integral y dA over A. Then this is equilibrium condition, sum of force along the x direction equal to 0. So, here from this equation you can say that Ek cannot be 0 because this is constant. So, the only possible way of making this equation is 0 is integral y dA equal to 0. That is integral y dA is nothing but the first moment of area. You can say that y bar equal to integral y dA by integral dA. So, the numerator is 0, that means y bar is 0. If y bar is 0, the neutral axis passes through the CG. So, for any problem easily you can find out the CG. So, once you find out CG, you can locate the neutral axis easily. And to complete this derivation, we need another equilibrium equation, that is called moment equilibrium. So, if we take this small section, the compressive force is sigma x dA will create a moment about the z axis in the clockwise direction, and this is a equilibrium condition for moment, net moment equal to 0. So, I can take mz, that is the external moment in the clockwise direction as positive, and the internal moment is created by the forces, that is taken as the counterclockwise direction, I have taken as negative. So, mz equal to minus integral dfy. So, we know already df equal to sigma x into dA. So, once you substitute this one, you will be getting Ek integral y square dA. So, integral y square dA is a very important property called second moment of inertia. I can write it as I. So, you can write mz equal to ek iz, where integral y square dA equal to iz, k equal to mz by e iz. But already we know sigma x equal to minus eky. So, you can reduce this formula, you will be getting finally sigma x equal to minus mz y by iz. This is called the bending formula, is also called as flexure formula. Next we are going to the topic called shearing stresses. Shearing stress is a force that causes layers of parts to slide down each other in opposite directions. An example of shearing stress is the force of two connecting rocks rubbing in opposite direction. So, you have shown figure also, when you are applying a load, the wooden plank breaks in the shearing pattern, because this is due to the shearing stress. So, we will consider a small section of a beam. This is normally what you are used is a positive sign convention. That is a Vy is the force acting on the left face upward, and Vy is another shearing force acting on the downwards, and there is a moment mz on the left face and moment mz plus Vy eta on the right face. So, let us take a cantilever beam. It is subjected to a point force. You take any section here, this is a shearing force, and assume the moment is also applied. Now, we have to see what are the resisting force on the other side. Because of this vertical force, there is a vertical downward force, and because of this moment, there is a moment acting in this direction. Now, we see this is not in equilibrium. Why? Because the net force is equal to 0 along the y direction equal to 0, because there is a plus Vy and minus Vy is there, it is 0. But if we consider the moment mz on this direction, and there is a another, sorry, this is mz. This direction, we will take this is positive, this is negative. So, there is another moment is also there. This is called these two equivalent opposite forces will produce the moment in the clockwise direction, that is Vy. I will call this place as eta, the distance. So, this also plus. So, that means this is not equal to 0. So, then this is not in equilibrium. So, what you have to do? There is a resisting moment, another moment is acting. Now, I can say this is in equilibrium. So, that is only it is shown in the figure. On the left face it is mz, on the right face it is mz plus Vy eta. Shear stress in beams. So, let us consider a small section of a beam shown in the figure. So, there is a shearing force Vy vertically acting upwards on the left face, and there is another shearing force Vy acting downwards, and there is a on the right face. There is a moment mz acting on the left face, and mz plus Vy eta is the moment acting on the right face. This is the positive sign convention normally we are using in solid mechanics. So, let us consider a beam, cantilever beam, it is subjected to a point load, and there is a moment also applied about the z axis. So, we will take any arbitrary section. So, I will show it separately. So, this is Vy is the vertical force acting on the left face, and there is a moment acting on the left face. So, this is nothing but the free body diagram. I have isolated the diagram from this one. I am showing the what are the active force and the reactive forces, and this is the resisting force Vy, and this is a resisting moment mz. Now, this is not in equilibrium, because when you see the force is in equilibrium, vertical force equal to 0, but if you see the moment is not equal to 0, because there is a MEZ moment is acting on the left face and there is a MEZ moment acting on the right face, and you can see there is a couple is also there, because this is a Vy, another is Vy. These two forces whose line of action do not coincide is called this will produce couple. So, we will call the distance as eta. So, I can write Vy eta, that is also in this direction. That means, if you add all these things, let us take this is positive, this is negative, this is also positive, this is not equal to 0. So, it is not in equilibrium. So, to make the beam in equilibrium, there is another moment is there. How it is in equilibrium. That is only it is shown in the diagram. One side it is MEZ, other side is MEZ plus Vy eta. The shear force Vy parallel to the beam cross section produces shearing stress sigma xy of varying intensity over the cross sectional area. Here the subscript xy indicates, the first subscript indicates it is the plane on which it is acting, and the second subscript y indicates the direction, that is sigma xy. Then the corresponding to vertical shear stress sigma xy, there exists a shear stress tau yx in the xy plane. This is equal to sigma xy at the point of the two planes. This is nothing but the complementary shear. Thus, the expression for the vertical shear stress sigma xy at any point in the cross section is obtained by determining the shear stress sigma yx on the horizontal plane. So, if you know the shear stress on the horizontal plane, I can find out the shear stress on the vertical plane. This is the procedure what you are following in derivation of the shearing stress. So, I have taken a I section which is symmetrical about one axis. So, here you can see the bending stress, how the bending stress varies with respect to the neutral axis. So, as already I told, the right side the bending moment is more, that is My plus Vy eta, that is only the bending stress, the magnitude is more in the right side compared to the left side. So, that you can see the diagram. At the neutral axis the bending stress is 0. So, we will take a small element from a distance y1 from the neutral axis. So, I have shown what is the difference in the stresses on the right side, that is Vy eta y Iz. Then this stress can be converted into force, elemental force, by multiplying with the elemental area dA. Now, this is not in equilibrium. To make this small section in equilibrium, a horizontal force is created, that is nothing but the tau Ix eta t. The eta t is the width of the section. The bending stress on the left and right sections of beam element is shown in the figure. This is what I told. So, at a point y from the neutral axis, the bending stress will be Mz y by Iz. On the left face, it is Mz y by Iz plus Vy eta y by Iz. And in order to obtain the shear stress at a distance y equal to y1 above the neutral axis, the portion of the beam about that point is considered as a free body. For equilibrium of the horizontal forces, the forces produced by the shearing stress sigma yx on the horizontal area of width t and the length dx, here we are using as eta as dx, must be equal to the difference in the normal forces of the two cross section. That is what I have shown here, the difference, that is Vy eta by Iz dA is equal to sigma yx eta t. And use the equation of equilibrium, sum of force along the x direction equal to 0. You can write sigma yx eta t equal to integral y1 to c Vy eta y by Iz dA. So, upon simplification we will get Vy by Iz t integral y1 to c y dA, and this is the formula for shearing stress. So, now we have seen the bending stress and shear stress derivation. So, we will see how to use this formula for solving simple problems. So, here I have taken a symmetrical I section. This symmetrical I section is symmetry about both the axes. So, if the symmetry is both the axes, means then you can easily locate the centroid. If the body is symmetry about both the axes, the centroid is nothing but the geometrical center of the body. So, it is there is a cantilever beam of length 50 centimeter there is a tip load of 20 kilonewton is applied. The dimension of the cross section dimension is shown here. So, the question is find the maximum normal stress in the beam, that is the bending stress, and also shear stress distribution. So, you know for cantilever beam the bending moment is always maximum at the fixed end. So, I can write maximum bending moment equal to 20 into 0.5, you will get 10 kilonewton meter. Then it is very easy to calculate second moment of inertia, that is coming 1620 centimeter power 4. Then find out the bending stress minus mz plus or minus y by iz. Here I used plus or minus y because it is symmetry with respect to both the axes. That is, the bending stress is either maximum at one fiber side, or the other is minimum at other fiber side. So, here you are getting plus or minus 43.20 MPa. Then after that, we are going to calculate the shearing stress. Sigma yx equal to Vy by Iz t integral yda. See, integral limit is y1 to c. Here the Vy by Iz is constant, so I calculated it is 12.34 Newton per centimeter power 4. Then you can write 12.34 by t integral y1 to c yda equal to 12.34 by t. That integral yda I can write as q. So, we will calculate q alone first. So, for take regions A, B, C and G. So, first we will calculate what is Q at A. Since there is no area above A, so the QA equal to 0, and next is QB. The area above the B is 10 into 2 and the centroidal distance is 6 from the neutral layer. So, it is 120 centimeter cube, and since B and C are located in the same line, so the QC equal to QB, that is 120 centimeter cube, and after that you can calculate QG also, it is 145 centimeter cube. The next is calculation of shearing stress. So, once you know Q, you can calculate shearing stress by using that formula. So, tau A equal to 0 and tau at B equal to the thickness what you do substitute is 10 centimeters, and at C there is a small difference between B and C, the thickness varies because B point corresponding to the bottom of the top flange and C point corresponding to the top of the web. So, that is only it is given 2 centimeter, and the shear stress at the centroid is 894.6 Newton per centimeter square, that is equal to 8.94 MPa. To calculate the shearing stress, once you note the Q value, then tau A can be calculated by using the relation tau at A equal to 0, then tau at B equal to 12.34 by 10, that is 10 is nothing but the width, we will call thickness into 120, it will be 1.48 MPa. Then tau at C is 12.34 into 120 by 2. There is a small difference between B and C, the only width is changing. B point corresponding to the top flange, the bottom of the top flange, and C point corresponding to the top of the web. And at centroid, the shear stress is maximum, it is around 8.94 MPa, and this diagram represents how the shear stress is plotted with respect to the neutral axis. It is varying parabolically. At the centroidal point, it is maximum. So, we completed the bending stress and shear stress expression. And next class, we will see the how to derive the bending stress expression for the unsymmetrical sections. Thank you.